Al-Khwarizmi, the father of algebra. In the first half of the 9th century, the great Islamic Caliph Al-Mamun asked the mathematician Al-Khwarizmi for a favor. He was asked to write a popular treatise on algebra to make the field more accessible. With algebra, if you need a reminder, being the process of manipulating equations to find the value of an unknown variable, or which in high schools today boils down to finding the x. Early algebra can already be found in the works of the Babylonians, the Greeks and the Indians. But Al-Khwarizmi produced something new. Instead of solving individual problems, he set out to exhaustively solve all possible versions of a specific type of equations, namely a quadratic equation. And he then also gave the steps to solve them. That is, he gave algorithms, a word named after Al-Khwarizmi. And Al-Khwarizmi also introduced the term algebra, from which the term algebra was later derived. And algebra referred to the technique, still commonly taught in high schools around the world, of moving terms from one side to the other side of an equation. So, we have a lot to get to. Let's start. Hey, good to see you. This is Stephan, author of In Search of the Sublime. On this World History channel, we'll trace humanity's relentless pursuit of scientific truth, moral excellence and enlightenment. You'll meet anyone from Mesopotamian astronomers and Indian yogis to Greek philosophers and Enlightenment scientists. And you'll meet them firsthand using primary sources, giving you valuable insights that transcend the surface-level understanding you get on other channels. So, go check it out for yourself. Let's start. Let's start with some background. The Babylonians had already found solutions to various equations as far back as 1800 BC. This included the quadratic equations that Al-Khwarizmi would later tackle as well. Yet, the Babylonians usually only gave answers to their problems without giving the algorithm the steps to solve the equation, and without giving proofs for what they did. A little bit like my own physics students. They don't want to write down the whole calculation, but only the answer. Algebra truly took off with the Greek mathematician Diophantus of Alexandria, who lived in the 3rd century AD, and he wrote the first proper work on algebra, known as the Arithmetica, from which the word arithmetic is derived. And in his work he studied a long list of number problems, and then after each problem he gave the solutions. Ahead of his time, Diophantus also used mathematical symbols to describe these equations. For instance, he used this symbol for subtraction, and this symbol for the unknown quantity, that is the x. And as it turns out, for more complex equations, these type of symbols become indispensable, for otherwise it is almost impossible to calculate with them. Yet symbols in mathematics would not be used again until the 16th century. Which means that Al-Khwarizmi in the 9th century also didn't use symbols. Instead, he gave his equations in full sentences. Take for instance the equation 10 minus x in brackets squared is equal to 100 plus x squared minus 20x. He wrote this equation as 10 less a thing, with a thing being the x, multiplied by itself, that is taking the square, is equal to 100 plus a square being x squared, less 20 things, minus 20x. And I don't know about you, but the moment I finish the end of the sentence, I've already forgotten the beginning. And here, by the way, we see a full list of the symbols used by Diophantus. We see symbols for 1, 2, 5 and 10, one for is equal to, one for the 0th power, the 2nd power, the 3rd power, the 4th power, etc. And as you might have noticed by now, Diophantus' notation resembles nothing like our own, so it looks very foreign and unclear to us. Take for instance this equation below. In Diophantus' notation it becomes this. Diophantus' work also had some serious shortcomings. For instance, he did not consider zero and negative numbers as valid solutions to his equations. Anytime a zero or a negative solution would be the answer of the equation, he just called the equation absurd or impossible. And this is likely because the Greeks equated numbers with the lengths of lines, and lines with zero or negative lengths do not exist. So the whole concept of a zero or a -1 seemed absurd to the Greeks. And Diophantus also didn't generalize. Instead, he solved every specific problem on its own, instead of finding generalized algorithms to solve all forms of a specific type of equation. The next great development in algebra came from India. In the 7th century BC, Brahmagupta, a great mathematician, finally allowed for negative solutions to equations. And he is also the first person, as far as we know, to use the number zero in calculations. More on this, by the way, in my upcoming lecture about the zero. And then finally we come to the man named Muhammad ibn Musa Al-Khwarizmi. That is, Muhammad, son of Musa, the Khwarizmi, meaning the man coming from Khwarazm, a city. Somewhere between 813 and 833, the great Caliph Al-Mamun in Baghdad encouraged him to write a popular work on algebra. It finally got the title Kitab al-Jabr wa al-Mukabala, or the Compendium Book on Calculation by Completion and Balancing. And it is preserved in a manuscript from 1342, which you can find in the Oxford Bodleian Library, in manuscript Huntington 214. We read in the introduction to his work, "In the name of Allah, gracious and merciful." This work was written by Muhammad ben Musa of Khwarazm. And then, that fondness for science, by which God has distinguished the Imam Al-Mamun, the commander of the faithful, has encouraged me, Al-Khwarizmi, to compose a short work on calculating by the rules of completion and reduction, confining it to what is easiest and most useful in arithmetic, such as men constantly require in cases of inheritance, partitions, lawsuits and trades, and in all their dealings with one another, of where the measuring of land, the digging of canals, geometrical computations, and other objects of various sorts and kinds are concerned. As stated here, it was also a popular work, made as easy as possible to make algebra available to a larger audience. And in fact, the work is simpler than that of Diophantus. Yet, as we shall see, the work still got an important place in the history of algebra. In fact, it transformed it into a mature subject. For instead of simply giving solutions to specific problems at hand, as Diophantus had done, Al-Khwarizmi set out to systematically and exhaustively solve general equations. What he did was the following. He solved quadratic equations by first dividing them into 6 classes, and then he offered systematic steps to solve each of these cases. And by the way, we'll go through all 6 of them later in the lecture. Today, such a procedure for solving an equation is called an algorithm, named after Al-Khwarizmi. Unlike Diophantus, Al-Khwarizmi also realized that quadratic equations can in some cases have more than one solution. And Al-Khwarizmi even figured out under what conditions a quadratic equation has no solutions, which happens when in his algorithm he had to take a square root of a negative number, and this does not exist. If you would type the square root of a negative number in your calculator, you get an error. To work with all these equations, Al-Khwarizmi used 2 operations, which were already recognized by Diophantus, but now they received their own names, namely al-Jabr or completion and al-Mukabala or balancing. And surprisingly, although both of these terms ended up in the title of the work and are continuously used in the text, he doesn't explicitly explain them. That has to be inferred from the text. Let's start with al-Jabr, which in Europe turned into the word algebra. This was the process of moving terms from one side of the equation to the other, causing the sign of this term to change. For instance, if we have x squared minus 6 is 23, this equation can be simplified by turning the minus 6 on the left into a plus 6 on the right. And this leaves us with the equation x squared is 23 plus 6. And 23 plus 6 is of course 29. So we're left with x squared is 29. And al-muqabala was the process of cancelling equal terms that appear on both sides of the equation. Take for instance the equation 8x is 6x plus 10. This can be simplified by subtracting 6x from both sides. In that case we get 2x on the left side and only 10 on the right side, and the equation becomes 2x is 10. And as you can probably imagine, a debate now exists among scholars on who is more entitled to be known as the father of algebra. Diophantus is a very obvious choice here, for he was the earliest, his algebra was more advanced, and Diophantus also used symbolic notation way ahead of his time. But other scholars support Al-Khwarizmi because of his exhaustive explanation of solving quadratic equations, which he also supported with geometric proofs. But in my opinion, they can both share the title. They both did very important things in the history of algebra. Now, let's look at the work in some more detail. Al-Khwarizmi sets out by defining roots, which is the unknown variable, the x, squares, which is x squared, and regular numbers. So 3 different terms. A square, he writes, is the whole amount of the root, that is the x, multiplied by itself, that is x squared. And then he combined those 3 terms into 6 types of quadratic equations. And by the way, quadratic equations are any equations that contain any or all of these 3 terms. Let's start with the first type. He calls it squares equal to roots. And as an example he says, a square is equal to 5 roots of the same. Or in modern notation, x squared is equal to 5x. We have a number of squares on the left side and a number of roots on the right side. Or another example, 1/3 of the square is equal to 4 roots. Or in modern notation, x squared divided by 3 is 4x. And the second example, by the way, can be reduced to the first form by multiplying both sides with 3, because then we end up with x squared is 12x. And he calls this reducing to a single square, because if we multiply both sides by 3, we are left with 1 unit of x squared. His second example was squares equal to numbers. For instance, 5 squares are equal to 80, or 5x squared is 80. And his third case was roots are equal to numbers, such as 4 roots are equal to 20, or 4x is 20. He then goes on to 3 more advanced combinations. He writes, I found that these 3 kinds, namely roots, squares and numbers, may be combined together, and thus 3 compound species arise. And these are ax squared plus bx is c, ax squared plus c is bx, and ax squared is bx plus c. The 3 combinations containing all the 3 terms. Let us start with the first one. Ax squared plus bx is c, or what he calls roots and squares are equal to numbers. As an example, he takes x squared plus 10x is 39. And then afterwards he gives the algorithm to solve this equation. And by the way, the algorithm here is equivalent to what we would today call the quadratic formula, the formula to solve quadratic equations. And we see this formula below, but Al-Khwarizmi still uses words. He says you have the coefficient of the roots, which is b, and we see that here, b divided by 2. This is multiplied by itself, that is, you take the square, which you can see here, then you add a 39, that is the c in the equation, as you can see here, Now you take the square root of this, and then you subtract half of the number of the roots. So again, minus b divided by 2. And in his example, where he used 10 for b and 39 for c, the equation now becomes 10 divided by 2 squared plus 39. Take the square root of the whole thing, minus 10 divided by 2. And this gives us the correct solution to the equation, namely x is 3. And we can check this for a moment by filling in 3 in the equation below. 3 squared, which is 9, plus 10 times 3, which is 30, gives us 39. So the left and the right side of the equation indeed become the same when we fill in x is 3. So this is indeed the correct solution. Al-Khwarizmi then generalized the solution even more by allowing the variable a, which you can see below. In this case, he said, we have to divide both sides of the equation by a, and here you see what happens if you do so. And then we end up with an equation which is similar to the previous type that we saw in the previous slides, namely x squared plus a constant times x is another constant, and for that type of equation we could again use the previous algorithm. Now the second case, ax squared plus c is bx, and the solution to this equation is given here. Notice here that plus minus sign. This means that we get a solution when we fill in a plus or a minus. That is, we get two positive solutions here. Take for instance the example x squared plus 21 is 10x. This can be solved by filling in x is 3 and also by filling in x is 7. You can test it out for yourself. Then Al-Khwarizmi showed that the solution to this type of equation becomes impossible when b divided by 2 squared becomes lower than c. And this is because in those cases, the algorithm gives us a square root of a negative number. And as mentioned before, that does not exist. Then Al-Khwarizmi gave proofs for his solutions. We'll discuss one example, which I really like. He again gives the same example, x squared plus 10x is 39. And then he draws the image seen on the left. The red square, he says, has sides x, meaning that the area of the red square is x squared. And the two green rectangles have a width of 5 and a length also of x, making the area 5 times x or 5x. And because there are two green rectangles, the total area of green becomes 2 times 5x or 10x. And from this we can write down the following equation. The red areas plus the green areas are equal to x squared plus 10x. And this is equal to the equation above. And we've already concluded that x squared plus 10x is equal to 39. So here x squared plus 10x must also be 39. Then Al-Khwarizmi focuses on the white square on the bottom left. This has an area of 5 times 5 is 25. And if we then add that white square to the area found above, we get the area of the entire square. It becomes x squared plus 10x, that is the red and the green area, plus that 25. And this must then be equal to 39, which we already had, also plus 25 is 64. So we've now found that the total area of the entire square must be equal to 64. Then Al-Khwarizmi set out to calculate the area of the entire square in one go. Each sides of the square are equal to x plus 5, so the total area becomes x plus 5 in brackets squared. And we've already learned that the total area is 64. So our equation becomes x plus 5 in brackets squared is 64. And this we can solve. We can take the square root of both sides, which gives us x plus 5 on the left and 8 on the right, because the square root of 64 is 8. And this can be easily solved. We find here that x is 3, for 3 plus 5 is equal to 8. And 3 is indeed the correct solution that we've already found earlier in this lecture. So in this way we have proved now that Al-Khwarizmi's algorithm is correct. After these proofs, Al-Khwarizmi discussed some other mathematical operations, such as the multiplication of positive with negative numbers. and also the use of brackets such as 10 minus x times 10 minus x, and also rules for calculating with square roots, for example. And then in the rest of the book, Al-Khwarizmi tackled many practical examples, as promised in his introduction. For instance, we read, "I have purchased 2 measures of wheat and barley, each of them at a certain price. I afterward added the expenses, and the sum was equal to the difference of the 2 prices, added to the differences of the measures." So very practical. And Al-Khwarizmi also discusses mercantile transactions. He calculates areas, dowries in marriage. He talks about emancipating slaves and also about issues of inheritance. We read, for example, "A man dies, leaving 2 sons behind him, and bequeathing 1/3 of his capital to a stranger." And thus unfolded the great work of algebra by Al-Khwarizmi. In the next lecture, we'll study the strange history of the number 0. Surprisingly, most of the early civilizations never invented the 0. We'll learn why, and then we'll explain why the Indians finally managed to treat the 0, the nothing, as a proper number to calculate with. But for now, if you want to know more about the history of mathematics or any other topic from world history, then read my book In Search of the Sublime. You can read it completely for free on worldhistorybook.com, or you can buy a physical copy on Amazon. Thank you so much for watching. Bye bye.